So we're going to finally get to the definition of the actual real definition of the definite integral today. And it's actually a limit of Riemann sums. So it says a left Riemann sum applied to a steadily increasing function over an interval is less than the true area. However, if the number of subintervals is increased, the error is reduced. So take a look at my function here. Is this function steadily increasing?
Yeah.
Okay. So if I want to do a left Riemann sum with two subdivisions from A to B, it looks something like that. Right? Now notice, is that the actual area under the curve on here? No, in fact, we can see the actual area under the curve is all of that. So look at how much is missing. Right? So what happens if we increase the number of rectangles? Well, notice what happens. So if I go all the way up to, say, 8 rectangles, 9 rectangles, there we go, 10 rectangles, do we still, is it exact?
No.
But it's close. But it's closer to the exact area, right? In fact, look at the left Riemann sum and look at the exact area of the integral. Closer, right? 2.366 versus 2.43. So how could we get even closer? More use more rectangles. So if I go up to, say, 40 rectangles, there's still some error, right? It's still under it. Right? It's harder to see them, but we're at 2.572 versus the exact 2.43. And so as we continue adding more and more rectangles, we get closer and closer. Right? So what we're going to be doing here is we're going to be looking at a limit of the number of rectangles. So it says, extending this idea to an ever-increasing number of subintervals, the true area under the curve is the limit as the number of rectangles goes to infinity. So we have this summation of, and notice we start with our first x and we go up to an infinite number of x values we're going to plug in because we're breaking into an infinite number of subintervals. And this is known as the definite integral from A to B. Okay. Now, calculating this limit is a non-issue because doing the definite integral will get to a way to do that. But interpreting this limit is an issue. We have to be able to interpret this limit as an integral. So the first example says, write a definite integral that is equivalent to this expression over the interval from 3 to 10. Now notice in the problem here, do you see a 10 anywhere? Do you see a 3 anywhere that's relevant besides the exponent? No. So there's an exponent cubed, but the limits here aren't inherent in this limit anywhere. So we actually have to know what our limits are. So we're going to write this as the integral from 3 to 10. Okay. So we're going from 3 to 10 because we're told over the interval from 3 to 10. Now our function here, notice it's 4x sub j cubed minus x sub j. So what is f of x sub j? What is our function here? Well, it would be 4x cubed minus x. Delta x, well, we've been writing that as dx.
Wait, what happened to the j?
So the j is part of the summation notation. This we're writing as f of x, our actual function. Okay? So this is a counter, essentially. It's an iterator. So it's the first x, second x, third x, fourth x, right? So when we're at the actual function, we dropped off that j.
No matter if it was like a different
It
number?
was I. That's not I.
No, but I'm saying if it was j is equal to like 2 or something like that.
Yeah, if we start someplace else, it's slightly different. We won't get into that. Okay. Good question. Yeah, so that won't be an issue. Okay, it says write a definite integral in, approximated by this left Riemann sum. Now, I underline that because it does matter. The fact this is a left Riemann sum actually has an impact. So, what is the width of each rectangle? 3. Okay, so this is our width, right? So if I'm just going to, sometimes the easiest way to start this off is to just imagine we have some function, right? Now, what is the function here, by the way? It's x squared, right? Because we have x squared. So our first x value here is 4, right? Because it's 4 squared. What's our next x value? So 4 plus 3, which is 7, right? What's our next x value? 10. What's next? And then there's some stuff, right? And then what's the last one? 19. Now, if this is a left Riemann sum, let's think about this for a second. Our rectangle would go right here and then over. Here and then over. Here and then over. This, this is a couple right in here. And then this last one, here and then over to the end of our interval. So what is the end of our interval? How wide is this rectangle? So what is this last value? 22. So since this is a left Riemann sum, we can write this as the integral. And we're going from what to what? 4 to 22. Exactly. So a left Riemann sum doesn't include that last number. So we need to make sure we add on one more width to get to the end of our interval. And our function here is x squared dx. Because it's a left Riemann sum, which means it's leaving off the last x value. This is f of 4, f of 7, f of 10, f of 13, f of 16, f of 19. It's a left, so that means there's one more x value we're leaving off, 22. How do we know it's 22? Because of our width here in 3.
Wait, how do you figure? I got the number outside. Here's how you got that.
No, this number is our delta x. It's the width of the rectangles.
So,
Yes.
what made you want to put a 22? Yeah, because 19. I have no idea why that's 22.
Because it's a left Riemann sum.
Yeah, so we
Okay. So our function here, let's continue, right? A left Riemann sum leaves off the last x value, right? And so the last x value would be 19 plus 3.
But we didn't have an interval or whatever.
Exactly. That's how we figure it out. The fact that it's a left Riemann sum, it starts at your leftmost x value, and it ends one before the last x value. So look at yesterday's notes when we did the table, or your problem yesterday. We always left off that last x value, right? The last x value is left off because it's a left Riemann sum.
Why can't we do all that?
Well, then it would only go up to 16. Let's do another example, and maybe it'll become clear. You're getting hung up on. I understand why you're confused. So now let's do the right Riemann sum. Okay. On a right Riemann sum, this last one, right, is right here. So let's let me make my x-axis. So my rightmost value is 19, right? Now that rectangle goes up and then like this, right? And we go back delta x. So this must be 16, right? And so on, right? That's the general idea. Okay. So we're at 16, and then we're at 13, which, hey, that's where that picks up, right? And then we're at 10, which is this. Then we're at 7. Then we're at 4, right? And then we're at 1. So on a right Riemann sum, we actually are leaving off the first x value in this information. And so we're actually, our interval here, when we write our integral, will be from 1 to 19. Our function is still x squared. Okay, so again, left Riemann sum, we're actually leaving off the last x value in this. It's called a series, but in this series, we're leaving on a left Riemann sum. We left out the last one was left out. We have to add on 3 more to get there, or whatever delta x happens to be. In a right Riemann sum, we're leaving off the first one, so we actually have to subtract 3 from the first one to figure out our lower interval. Okay? So does that kind of answer?
So we're just adding 1 to the right.
Adding, not 1, adding delta x. For a left, we have to add on to the last one. For right, we have to subtract from the first. That's the
So the first
simplest
one would
right.
be like -2?
No.
No, I know it's 1, but like if you...
Yeah, like let's say this said 4 minus 3 squared, right? Then the one that's being left off would be -2.
Yeah.
Yep. Okay. All right. I've got an integration rule here. So look at the integration rule. What's going on here?
Wait, you didn't write the integral though. You just wrote
The integral just came.
That's integral. Don't accuse me of things. That hurts my feelings.
Did you do the other one?
So you gotta wake up. Yes, I did the other one.
Come
Do
on
you need
now.
glasses, Julian?
I have.
Put them on. The squinting's hurting my eyes. Okay, so this rule basically just says, remember, if we have a constant times a function, we can pull the constant out.
Oh, so then it'd be
Okay.
outside.
So let's kind of prove this. Let's prove this. It says, show the following is true by using geometrical areas to find the exact end of the curve. We're not going to use Riemann sums. We're going to go back and do actual geometric areas. So let's graph 5x plus 5 on the interval from 2 to 5. So I'm worried about 2 and 5. Now when x is 2, y is 2 times 5 is 10 plus 5, 15. So this point right here is 15. What's wrong? And then plug in 5. So we get 25 plus 5, so that's 30. We come up here, and there is 30. And it's linear, so I know it's a nice straight line. And so we've got a trapezoid. Okay. Trapezoid. So the integral from 2 to 5 of 5x plus 5 dx is equal to 1/2. Now the two bases, remember, are the parallel sides, so we've got 15 and 30 times the difference in the bases, so these are 3 apart. Okay. So we've got, what, half of 45 times 3. Calculators can come in very handy here, right? Otherwise, we should get 67.5. Okay. Now let's do this one. It says 5 times the integral from 2 to 5 of x plus 1. So we want to graph x plus 1 from 2 to 5. So let's see here, x plus 1. So if we plug in 2, we get 3. Plug in 5, we get 6. So we've got a trapezoid. So the integral from 2 to 5 of x plus 1, let's see here, base, let's see, we have 1/2 times base 1 would be 3, base 2 would be 6, times the height of 3. And so we get 9, 27 cut in half, 13.5. So 5 times the integral of from 2 to 5 of x plus 1 dx would be 5 times 13.5, which is 67.5.
You can take the 5 out.
So if there's a common factor, we can factor it out and pull it, and we can, it's called migrate across the integral, bring it out of the integral.
But then we couldn't.
That's what you did with those weird ones when you first started.
When we were doing the antiderivative, right, we were able to bring the constants out. So for the definite integral, just like the indefinite integral, right, we can bring constants out. It works the same way.
But
Okay.
it wouldn't work if it was like 2x plus 2.
If there wasn't a common factor, then yeah, you can only bring constants out. They have to be a common factor.
Okay.
Yeah. And you can notice we can't actually migrate an x out because that would change the graph. It would change things a lot more. Okay. All right. So there's really no answers per se to give on this because I don't know, they require the actual work to be shown, kind of like you're writing an integral. So I don't want to give any of that away. But as you finish, like I would recommend after you finish the first 2, maybe come up and check your answer, and then pay attention to who's checked, and you can check with them or whatever.